Thank you. I'm just dealing with some non-trivial topology. Okay. All right.
Sorry, just before you start, I just wanted to say that there are mics all over the place. So it'll be nice if people try to use the mics, then people on Zoom can hear us. And also sometimes when people ask questions on one end of the room, it's not audible on the other side. So maybe we can try to use the mics.
Okay, so I'm going to start today by talking about modular data for the Rindle wedge. Recall that the modular data is defined when I have some algebra, some von Neumann algebra, and some state. Okay, so the state clearly here is going to be the vacuum state. And one thing that I didn't talk about, although it has been discussed, is that the vacuum state is cyclic and separating for localized regions. It's also, it's not much of a stretch, cyclic and separating for the wedge region. So what is the wedge region? So if I imagine, Minkowski space with null coordinates, like this, and I draw the U and V plane, and the Y I've just suppressed, then the wedge region is just this region here. Okay? So it sort of goes off to infinity, but it's localized enough so that you can prove that it's cyclic and separating. The vacuum is cyclic and separating for the algebra of operators associated to this wedge. Okay? And so our goal is to find the modular operators, right? So the modular operators were defined as follows. J delta to the 1/2 acting on the vacuum gives back a dagger of that operator, and this is for all elements in the algebra. Okay? And so I'm not actually going to prove this. It takes a little bit of time, and we don't really have time. I'm just going to give you some indication why it's true. And in particular, I'm just going to tell you what the answer is, and then we'll just check. Okay? So the modular data, the first part is this anti-unitary operator, and of course we have a nice anti-unitary operator in quantum field theory. We have the CPT operator. The right thing to do is to do the CRT operator, where R is a reflection in this X direction. So that's the X direction. And R is just a reflection this way. In time, actually, it's a reflection like this. Okay? And C and T are the usual things, and the T makes it anti-unitary. Okay? It makes it anti-unitary, and of course, the important property that we want to check is, or one of them, is that it leaves the vacuum invariant, and of course that's the CPT theorem. Okay? So that's part of the data, and then the other part, delta, I'll give it to you as follows. Delta to the IS is e to the minus IS 2 pi k, where k is the boost generator in quantum field theory in relativistic quantum field theory that fixes this wedge, right? So it fixes the wedge. So in particular, it has okay, let me draw another picture. Right, so the generators of the boost have the following picture. There's some killing vector whose flow lines look as follows, like this. And so, this is holding fixed this wedge region. And in particular K, so K is this boost, and we can write K always as the integral of some local operator, the stress tensor, over some time slice, T is 0, T mu 0. Okay, and C mu here is just this vector. It's killing vector. Okay, yeah.
Could you just clarify, does this operator actually really act on the entire space-time or just on the vector?
Oh yeah, no, the entire thing, yeah. It's
I can see that was good. Still even have inside and outside, so the entire space-time. So it's continuable inside. Yeah, for example, there.
well, it's a conserved charge, right? So it's something that I can act wherever I like. Yeah, so I picked some T as 0 slice, but I can move it around with no cost. Yeah, so good. Yeah, and so now, so now this has the property, right? The outcome of Tomita Takasaki theory that it clearly fixes the wedge. So my notation again. Yeah. IS. Right, so it fixes the wedge. And also, you know, the J takes you to the commutant, or it takes you to the other wedge region, which you might expect is the commutant. Now we should really, you know, understand this equation, because that's the defining equation. And we can do that because we can do that as follows. So if you look at here, there's a half, right? Whereas I defined this with an IS. So this is a unitary operator. This is not, but you know, I can get to a half by setting S to I or minus I over 2. And when I do this, this becomes, it's not hard to see that this is going to become a Euclidean rotation, right? So the sort of Wick rotation of a boost is some Euclidean, just regular rotation. And so, for example, we can draw the following picture where we sort of complexify time. So this is my x direction here. This is going to be my imaginary time direction now. And then coming out of the boards somehow is the real time. And so this is meant to be perpendicular here. And then so on this axis here, in this direction out of the board, we have our UV coordinates. Compressed a bit. And in the imaginary direction, we have some Euclidean coordinates, okay? And so in particular, the boost in real time becomes a rotation in Euclidean time, okay? And I picked the normalization here, this factor here, so that when I set S to I over 2, or whatever I have to do, I guess minus I over 2, then this becomes a pi rotation, right? So this factor here, K is, you know, naturally normalized to be the rapidity, and so this, when this is pi, this becomes a pi rotation. So in fact, the delta to the 1/2 is a pi rotation, right? And now you can see how this equation is going to be solved. We take an operator in this wedge here, A. We act with a pi rotation. We come over here, right? And then we apply J, and J pushes us back over here. So, and in particular, so this is J. Let me draw use some color here. This way, this is delta to the 1/2. And in particular, J is what's turning A into A dagger, right? So at the end of this journey, it's A dagger, not A. Okay. All right. Yeah. Yeah. So this is like, you can sort of think of it as the algebra in the other wedge, but it's equal to the algebra prime, right? So that's the commutant, yeah. And J is taking things from here to here, right? So that's what it does. Okay, so you can be a little bit more explicit about this. You can put in particular operators. This result is due to Bisignano-Wickman, very famous. Bisignano-Wickman, and they worked within the Weidmann framework, so they had field operators, and these operators were actually field operators. Okay, so they weren't bounded operators like I want to work with, but that's okay. You can still go through all of this in that context. And the important point is that for those correlation functions, you can do this by some analytic continuation of the correlation function. And to do that, you need your correlation functions to satisfy analyticity, obviously, and that comes from this spectrum condition, which has also been discussed. Right, okay, so good. So indeed, Bisignano-Wickman constructed the modular data. That's good. They also showed the following result, which I've already alluded to, is that you have Hague duality here. So, remember this was something we may or may not have added to our axiom set. Here is a case where you can just derive it. So perhaps more generally, you should try to derive this thing. In particular, that's the title of the paper, right? So this was the more important property for them, okay? Not the modular data. And the other thing you derive is that the center is trivial. It's just complex numbers. So this is what they derived. Now, you may have heard of the much more physical manifestation of this mathematics, which is Unruh radiation. So let me say a little bit about that. So Unruh radiation pertains to observers that are uniformly accelerated, and such observers live on these lines, right? So they live on the generators of this symmetry. So these are all Rindler observers, and their time is given by this boost time, right? So their time is boost time, which of course we know is now modular time. And the other thing we knew about modular time is that correlation functions satisfy this KMS condition. The KMS condition is linked to thermal physics, and so that's why these Rindler observers see thermal physics. They see some temperature. Right? So you get this thermal bath, and it comes from this result. Okay, questions? Okay. Yeah, good. So I forgot to say one thing, which is important, a result of this. We have the modular operator now. We can ask, what is its spectrum? Okay, and the spectrum of the log of the modular operator, which is the boost operator in quantum field theory, is just the real line. Okay, and so you can see that in various ways. For example, if you think of about these Rindler observers, you can think about excitations of these Rindler observers, and just by moving them around, you can create arbitrarily low energy and high energy, where energy here means this boost energy. Okay, and so the spectrum of the boosts is all of the real line. That doesn't necessarily mean we have type 3-1, because remember, for that, we had to take the spectrum over all possible modular operators. But with some other arguments, you can at least convince yourself that at very short distances, any state should look like the vacuum, and so should still have this property. So all states will have this kind of spectrum, and so you'll find that the von Neumann algebra is a type 3-1 von Neumann algebra.
Sorry, Tom, why isn't it enough to conclude that it's type 3-1? Because as you said, all states have a continuous spectrum. So, you already know that. What is the subtlety?
Oh, no, I'm just saying, just knowing the spectrum of one modular operator is enough, not enough.
Right. But you can look at.
But then I made some more hand-wavy argument that it's true in general. I guess the subtlety is that you have to give some teeth to those arguments.
I see. So it's not enough to just impose the Hadamard condition on correlators near. The kind of argument Raghu was giving, and then say that tells you the model.
Yeah, no, I think that's enough. I think it's. I'm not saying it should be obvious. I'm just. Okay. I was just saying this is not enough.
Okay.
Yeah. So Hadamard is something else. Then yeah. 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 That's right. Yeah. Yes, cyclic and separating vectors. Yeah. Yeah, I mean, in some fixed representation, that's okay. But there are also ways to get around this as well, and Nima knows this well, and so you can ask him about it. Yeah. Yeah, so they were using Weidmann axioms. So they had like some axioms for fields. No, no, this is purely quantum field theory. Yeah. I think most local quantum field theories. Yeah. No, I think gauge theory should be okay. Yeah, so good. This has been discussed at length at this thing. So these theorems are very strong, right? So they tell you that the center is trivial, and they're based on very minimal ingredients. So my feeling is that even in like a gauge theory, even though if you have some lattice regularization where there's definitely a center, somehow when you take the continuum limit, the center sort of goes away. It goes to the sort of the cutoff. And so for some reason, yeah, so as long as you get back things like Lorentz invariance and these things, yeah. So I think, yeah, but for gravity, of course, that's a completely, yeah, I don't even know how to start formulating that. Okay, good. So one more, yeah, I want to say just really quickly one more thing. If you can do better than this if you're in a CFT and say CFT in flat space or on the cylinder or some conformally related space, and you think about diamonds. So diamonds are the intersection of the past and future of 2 points like this. Then there is a conformal killing vector that leaves this diamond invariant, has some flow like this, right? And there's some flow outside as well. This. So associated to this, you'll be able to find modular operators. Right? So in particular, J will be some anti-unitary operator that takes you from this diamond outside of it, and delta to the IS will be just this flow, okay? And so you get modular data in the same way. You also get Hague duality for these local regions. And you can show that the center is trivial. Okay, good. All right, so now I'm going to move on to a quick application of this modular theory, which is to proving the average null energy condition, the ANEC. Okay, so the ANEC, what is the ANEC? So let's just talk about, for simplicity, the ANEC in Minkowski space, okay? That's perhaps not the most interesting one, but let's start there. So it's a quantum field theory constraint. That says that integral dv tvv, so I can use my uv coordinates still, we're in Minkowski space, along the v direction at u is 0. This, from minus infinity to infinity, should be a positive operator, which means if I sandwich it between two states in the Hilbert space, I'll get a positive number. Okay, okay, so this is a constraint, we believe is true. And in particular, it's an important constraint when you think about taking matter and coupling it to gravity. Because if you have matter that violates the ANEC, you can violate causality in certain settings. So it's sort of an important constraint if you want to couple the theory to gravity. And so I claim this inequality comes directly from modular theory. And it's actually quite easy to see that, or like where that comes from. In particular, if I just take a two-dimensional theory, right, and I consider two wedge regions in Minkowski space, like this. So I have some A algebra and some B algebra, and B is a subalgebra of A. And they're sort of translated in this null direction. So this is the V direction, right? And so, yeah, I'm talking about algebra of operators in B or algebra operators in A, okay? And, you know, because these are just wedges, they're both just wedges, we know what the modular operators are, right? So we know that the log of delta A is just -1/2 pi Ka, which is, this is the boost associated to the A wedge. And then similarly for B, KB. And it's not hard to see based on the Poincare group that the difference of these two boosts is just a translation in the null direction. This is just a number, delta V. That's this deformation, right? So delta V is that length. And times PV. And so we showed previously, or we discussed, I didn't show it actually, that the modular operators have this order relation for algebras when you have inclusions, right? So when B is in A, you always have this, okay? And so we can just, you know, use that for here, and we find that PV is positive, okay? Now, this was kind of a bit silly because this is just, sorry, when I said PV, I gave, yeah, sorry. PV is integral dV TVV in 2D, but it's also the generator of null translations. And of course, that has to be positive by the spectrum condition. So it's already obviously true, okay? So we didn't learn anything new, but we do see that, you know, there's some connection between this modular theory, positivity, and these energy conditions. And so what you have to do in higher dimensions is a little bit more complicated. So, yeah. No, it's, yeah, so it's an unbounded operator, so yeah, it could be divergent, yeah. Yeah, it's positive, yeah. Yeah. Yeah?
So, I don't understand what, didn't we know that PV was positive? Why
Yeah.
do we need modular theory?
Well, we don't, but I'm just saying, I said that, yeah. So, yeah, I said that. So we know it's positive, but we can also write it as a difference of two modular operators. That's suggestive. Now we're going to do that in higher dimensions, and we'll get something new in higher dimensions. Yeah. What's that?
That horizon is supposed to be a black hole horizon? Or?
Well, it can. I'm just doing Minkowski space for simplicity. But yeah, it can be a black hole horizon. Yeah. There's nothing in principle wrong with that. So yeah. Yeah, so the thing that I'm going to tell you, you can prove along black hole horizons in higher dimensions. But I'll just do it in Minkowski space, okay? I'm not really sure why. I mean, it's just fine. Okay, so now I go to higher dimensions. So my pictures get a bit more complicated. So I still have my U and V directions. I'll draw them like this. But now I have another direction that I'm going to try to draw three-dimensionally. That's really bad. Try it like that. So that's Y. You know, and the Rindler wedge is some null plane here, some null hypersurface here. H. So I'll call this H. Okay, so this is meant to be null. It doesn't look very null. Oh, well. And so what we're going to do in higher dimensions is we're going to take two regions. One which is all of the future of H from this point. We're going to take two regions of the horizon, right? So this horizon extends down here. So this is some subregion of the horizon. And we're going to take another region which comes from deforming this this boundary or the edge like this, okay? So we're going to deform it in some particular way. And there's going to be some function, delta V of Y, that specifies that. Okay, and so you can sort of see why I'm doing this. In higher dimensions, I could have done a deformation where I do a uniform deformation, and then I have two Rindler wedges, and then I get the modular operators are two boost operators, and I get the same thing that I just got in 2D. I just get the null translation operator, which we know is positive. The ANEC is kind of much more localized. We're just integrating over a single line from -∞ to infinity. So yeah, it's a bit misleading here. There's this Y here, and the Y is fixed, okay? So it's just, this is a single line. And so how are we going to get a single line? Well, we're going to try to sort of localize around a point by having this sort of bump here, okay? So we're going to try to localize around this point over here. So now we're going to define two algebra of operators, one associated to the deformed region, B, and one associated to the undeformed one, A, okay? Yeah. Yeah, so I've just drawn a region on a horizon, okay? To actually specify the algebra of operators and the region associated to that, you have to take the causal completion of that. So in particular, so A will be the Rindler wedge, okay? So the algebra of operators for A will just be the same Rindler wedge we were just dealing with, okay? B will be different because of this deformation. B is associated to some region I'll call WB. So WB you can think of as take this horizon, restrict it to this function, V is bigger than delta Vy, and then do this causal completion. Okay, so this horizon is some closed, subset of Minkowski space. This causal completion will give an open subset where this is at the boundary, and it will fill in this thing. In fact, you'll basically take this region and shoot null geodesics backwards. There'll be caustics. It'll be quite a complicated region, but it's some space-time region. Yeah. This plane, yeah, that's right. And then I'm trying to draw 3 dimensions, so there is another direction there. But yeah. So you sort of fill in the U direction. There's nothing in the U direction, but then when you do this, you'll get some region. Okay. And so these are my two algebras. And the claim is going to be that so what we're going to find is that the log of the modular operator for for B minus log of the modular operator for A is going to look like some version. It's going to localize to integral T++, and so we'll prove the average null energy condition, TVB. Sorry. So that's the goal. Is that clear? Is there questions?
It's sort of weird that the left-hand side has more to do with B positive, but the right-hand side has to do with volt.
Sorry, where's the right-hand side? This thing?
No, the right-hand side.
No, because these are they're full modular operators, so they exist on both sides.
Oh.
They pertain really to the algebra and its commutant.
Oh.
Yeah, so yeah, you're right. Okay, so that's the goal. Now, originally, I wrote a paper with Onkar and Rob Lee where we did this, but we used the following method. We used sort of path integral methods to write down these modular operators, and we did some perturbation theory in the shape. Okay, so we did some deformations, inserting the stress tensor to move around the regions, and we did some perturbation theory, and after some chugging, we found this popped out. Okay. Now, since that argument, there's been many updated arguments. So there's sort of more refined and better ones that don't involve like the path integral or anything like that. So I will try to present those arguments. Yeah. Yeah, delta V. Yeah. Oh yeah, that's the entire horizon. Yeah.
It's a log. It's a log. It's not an equal.
Sorry.
Sorry. Okay, that's right. Okay, but in any case, sorry, it depends on delta.
Yeah, delta V of Y, yeah. Mm-hmm.
And then the right-hand side is just
there's a twiddle here, so there's actually an integral over the Y direction, smeared by delta V of Y, and then you sort of, you can localize it as much as you like. The argument was very general. It was some path integral, Okay, so I'm going to try to present an updated argument. And this is really, I think, spelled out, most clearly by Witten in some notes that are not easy to find, actually. And Cassini et al. Made some similar comments. And then with Anthony, wrote a paper recently where we also spelled this out a little bit more. Okay, so So we want to associate an algebra of operators to this sort of null region. So the issue with doing that is going to be, well, we first want to associate an algebra of operators to the horizon, okay? And we sort of know that that's not always a good thing. So in particular, let me start with some set of operators that's associated to this deformation. I'll call it L. So it's this set of, say, local operators. Could be a bunch of them, where X is on this horizon, restricted to this region. Okay. So these are not really operators, as we talked about. They're sort of quadratic forms. You can try to smear them on the horizon. For a free theory, then that's good enough. Actually, you can smear them and get good operators. But in an interacting theory, you can no longer do that. So you have to do something else. You can still define these as quadratic forms, so you can define matrix elements of them, and that's fine. And in particular, for each of these, there's some set of vectors for which this is well defined, and that defines some domain associated to that field. Okay? And so what we want to do is we want to understand what is the commutant of this set of operators. Okay? And so we can define that. It's not the same as how we've been talking about the commutant, because we have to be careful about this domain issue, but it's the set of operators, possible operators, that commute in matrix elements, in all matrix elements that make sense, essentially. 0, eta 1, eta 2 is in this domain, and A leaves invariant the domain. Okay, so there's some technical thing here, but basically that lets you define the commutant. This algebra that you define is not actually a von Neumann algebra because we had to add all these other conditions. But then you can take another commutant of what you get from that. So I'll call this L prime. You take another commutant, and then you get a von Neumann algebra. So L double prime is the von Neumann algebra associated to these deformed cuts, right? Delta Vy. So this is what I was calling over here, B of this thing. I'll use a different notation now just to be confusing. But yeah, so I'll just associate it to one of these cuts. We'll have a von Neumann algebra like this, okay? And it's defined in this way. Yeah. Yeah, because of this domain conditions here. Yeah, so you won't be able to multiply two of them. You have to check the domain condition. I think. Yeah, right. Yeah, I'm pretty sure it's not a von Neumann algebra. It doesn't really matter. Yeah. Okay. Okay, so this is my algebra of operators. And the nice thing, why am I doing this? Well, the nice thing about this is I can define a null translation, which is sort of depends on this delta V, right? This is eventually the thing we want to show is positive. Integral TVV, V times this deformation, and then an integral over Y, like this. So this is not a conserved charge, it's not a translation operator, it's just this operator, okay? But it's not hard to see that you can act with this operator on this set of operators, and you know what it does to these operators, because they're localized on the horizon. So, yeah, because they're localized on the horizon, we can take this operator. So if we have some operator over here, y of x, we can take this sort of funny null translation operator, we can expand it near this line it goes through, and then it looks like a null translation. There's some corrections, and you can systematically compute those corrections. And so as a result, you can sort of write down the following equation. P delta V, Y, acting on one of these operators, I here, V, Y, results in a translated operator where we translate by some amount that depends on Y, right? And this could be a different operator, so that's a different label there. And in general, it could be a sum or something. Yeah, and it's a different operator because of this expansion thing that I mentioned. Okay, but the point is it's a local operator, and so that means I now know how these operators, these translations, these sort of funny, wiggly, non-uniform translations, we know how they act on this set, and the von Neumann algebra was defined with respect to that set, so that means we actually know how it acts on the von Neumann algebra. So we write the following. E to the I, E delta Vy, acting on completion. Oh, I didn't write it. Acting on A of 0, so that's the wedge algebra because there's no deformation, is equal to the deformed algebra. Okay. So that's what we wanted to get at. Okay. Good. Now, the other thing we need is that P delta V of y needs to annihilate the vacuum, right? Why is this? Well, here's the following argument. If I take the Rindler boost, or just the boost associated to the undeformed region, I'll just call that delta omega, I'll call it, sorry, delta A, IS, A of 0, and I apply it to P, delta V. This is just a boost, so it's quite easy to see what it does. It just, it just gives you some factors of e to the 2 pi s, and it shifts, and you can scale those factors out of this integral, and it just gives you an overall factor of e to the 2 pi s, right? So that's just the boost weight. This is the boost weight. It's a funny normalization just because of the modular normalization times. So that's easy to establish. But that means if I act with, so if I act with delta IS on P delta V on the vacuum, supposing it's not 0, then I just get e to the 2 pi s times the same thing. So that means this new thing that you get, which may not be 0, is an eigenstate of this boost. This boost is a unitary operator, so all eigenvalues have to be phases. This is not a phase. That implies that this has to be true. Okay. So there I didn't use anything about positivity, I just, because that's what we're trying to prove. Okay, so then, yeah. Yeah. Yeah.
Okay. And what was A of delta V if you just location for that?
Yeah, so I was, sorry, I forgot to label it. So this is really L of delta V double prime, right? We can also do L of 0 double prime, and that will just give the wedge. Just the wedge, it's like the undeformed wedge. And so that is this A of 0, which is the other algebra. Yeah. So scry? Oh, let's talk about it after. Yeah, that's a good question. Yeah, okay, I haven't connected this to that story, so maybe we can talk about it after. Yeah. Yeah, I think it might be called that. Yeah, I'm not sure actually. Yeah, this is like this, quadratic, these sesquilinear forms, and so there's a whole theory of these things. Yeah. Well, it's unbounded, so it makes it a little bit different, I guess. Yeah.
Since you're being interrupted anyway.
Yeah, sure.
I completely missed why we were done at the bottom of that.
Oh. This was to prove.
Why is it? I mean, over there
It was just clear. Yeah, here it's not clear because it's not a conserved charge. Right, so if this wasn't there, it would be totally clear. In the presence of this deformation, it's not clear. Because we just don't know what those modular operators are. Right? We do now. I know what they are now, but we didn't know. No one said they had to be this. Yeah. Okay, so anyway, these two conditions, the fact that the algebra is shifted by these unitaries and the unitary holds fixed the vacuum, means that the modular operators are actually covariant. So this means that I can apply delta V of y So the modular operator for the A region, or the log of the modular operator, that's what we really want. And I'll get the modular operator of the B region. And the reason we needed this condition, right, is because the modular operator depends on two things, the algebra and the state, right? So that's why we needed that. Okay, and so now, now all we have to do is expand in delta V, linearly in delta V, so we just get I times the commutator delta Vy Ka is equal to Kb minus Ka. Ka is just a boost, so we know how it acts on P delta V. You just get another factor of I, and you get P delta V of Y is just Ka minus Kb, which is positive. Okay, so that's the proof. Okay, so questions?
Yeah, I have a question.
Yeah.
So in this equation, delta to the is p delta to the minus is equals e to the 2 pi s,
Yeah,
this one,
yeah.
you're only using somehow some commutator between p and the boost. Between the stress tensor and the boost, is
Yeah,
that what
the
goes?
stress tensor and the boost, yeah.
And the boost, okay.
That's it. Yeah.
And could you say one more time how you got the first equality on the next board between, why do you?
Yeah, so it's just modular theory. So modular theory gives you a way to define these modular operators, right? And so if you go through those definitions and you add some unitaries in there, you'll see that the definition of one goes to the definition of the other. And so it's covariant, so you can map them. But for that, you do need e to the I P delta V, vacuum is vacuum. You need that.
Regarding why this p delta y is acting as this roughly like a translation.
Yeah.
So the v integral is done over the full v line from minus infinity to infinity, but they're sort of localized in y, right? The definition of p on this board, just to the left of the screen.
This one here?
Yeah.
No, there's an integral over y here.
Yeah, so the v integral is unrestricted.
Yeah, yeah.
So why couldn't I have also tried restricting the v integral? Because you only need to shift the operator sort of at the horizon, at the bifurcation line. Would you get something similar? Like, because I think here the idea is
Yeah, I hope you don't, because that shouldn't be, there should be no positivity for that. That's the issue.
Right.
I mean, it's an interesting question though, because I don't have an immediate answer why it doesn't work. Well, maybe it's not I mean, this is somehow meant to be a well-defined operator, and what you say is not. It's like the half modular Hamiltonian, which is not a good operator.
right, but
So we can't take e to the I of it, for example.
right, but at least from this presentation, it's not 100% clear why the y integral could be bumped, but the v one could not be.
Well, I mean, the way that I proved this is you can't have a V bump, I don't think. Well, maybe you can. Yeah. Oh, yeah, we'll also not annihilate the vacuum. Yeah, maybe that's, yeah. Yeah, I mean, you can try. Maybe it's a good exercise. Yeah. 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 It's not positive, no. Well, I know, but let's say this argument shows that it's positive, then there's some hole in this argument, I guess. I think that's, yeah. I mean, there's all sorts of things like that are not completely, I would say, so for example, this would not fly in an algebraic quantum field theory conference. Because I'd have to say, I don't know. I don't think they'd be happy. But yeah, I think we're getting closer. We're to the point where it will fly. So yes. Yeah, that's totally true. Yeah, so even just writing this is not okay. So at that point, I'm willing to walk away from it.
But the P is not operating.
Well, according to them, yes. Yeah. Well, I think whether that's defined or not, I think might, I'm not sure if they'd be happy with that. But anyway, so I think it's, my personal view is it's getting closer to where they will be happy. But yeah, so I'm quite happy with this argument. I think it's like the most sophisticated, the most advanced one that there is. Yeah. Okay, other questions? Yeah. Yeah. Yeah, yeah. Uh-huh. Yeah. Yeah. Yeah, I mean, the modular operators are there. Well, I mean, it's the half-sided module inclusion, which I think I've always believed is there. And that has the same thing. Yeah, but you can have a set of half-sided module inclusions, and I've always believed that there is. And I think it's infinite dimensional. Yeah. So, yeah. It's interesting. Yeah, that structure is really interesting. Yeah.
I don't know if you were planning to talk about like generalizations to things other than Minkowski space.
Sort of. Not really. No, I wasn't.
I mean, that's like obviously there's the AA neck.
Oh,
and
yeah.
Is there any hope of using these techniques to do something like that, or does it seem like really just
Yes. So not really. So we just need a horizon. You can make the argument on some bifurcate killing horizon where you have a natural vacuum, like a Hartle-Hawking state or something, and then you can make the argument.
Okay, so that presumes a killing vector.
Yes.
Yeah. So, but
Yeah.
in the absence of
Yeah. So in the absence of that, then there's this whole story about self-consistent acoronal ANEC,
right.
where you push to the point where hardly any spacetime satisfy your assumptions. And there's something called a splitting lemma, which when it does satisfy the assumptions, you can split the spacetime in two. It's very suggestive. You could make an argument there, but I don't know how to. Yeah. But this part of the issue is I don't know what state to use. There's no like nice state. So yeah. So just super translations are in a gravitational theory, right? Okay. To the which? Uh-huh. Okay, I don't know. I'm not sure what to say. Yeah, so maybe we can talk about it later. Yeah. Okay, so I was gonna do something new now. I don't have much time, but well, I guess I will start at least because I had planned to say a little bit about gravitational von-Neumann algebras. I wanted to get to type 2. So I've seen type 3, and I wanted to give some type 2 case. So we'll see how far we get. So, yeah, let me start. Any questions? Okay, let me go here. Okay. So okay, so this is sort of a series of refinements of work, sort of starting with some ideas of Lou Leuthauser, which introduced sort of emergent von Neumann algebras in ADS-CFT. And in particular, they sort of found an emergent type 3 von Neumann algebra. Then Witten refined that discussion to something called the cross product, which gives a type 2 von Neumann algebra. And then there were lots of follow-up work. CPW, Chandrasekaran, Pennington, Witten is the paper that I will sort of follow closely. And although, you know, many of these discussions are in the context of ADS-CFT, but it turns out you don't need ADS-CFT at all. It's just some general statement about semi-classical gravity in some limit. Okay, so we're going to think about semi-classical gravity in the G Newton goes to 0 limit. And I'm going to think about negative cosmological constant just for simplicity. There's some technical issues if I don't do that. And say D is 4. So in particular, I'm going to consider fluctuations, linearized fluctuations of gravity in this limit, that's what you get, plus matter around some black hole spacetime. So I'm going to set boundary conditions so I have some black hole around a two-sided black hole, ADS, Schwarzschild black hole. And there's some temperature, and that temperature is above the Hawking phase transition. Okay, and so, you know, we draw this Penrose diagram, that black hole. And looks like this. There's two asymptotic boundaries, and near those boundaries you have some sphere, some S2, and there's some point on this boundary that I'll call the 0 of time. So there's a left 0 of time, and there's a right one, and I also have a S2 here. So there are very big S2s near the boundary, but yeah. So usually this is like set up for ADS-CFT, but I'm not really going to say anything about ADS-CFT. Okay, so now, you know, these sort of fluctuations of graviton and matter you expect should be described, at least in this limit, by a local quantum field theory. So in particular, I'm going to use algebraic quantum field theory to describe it. And I'm going to think about the algebra of operators. Localized to, you know, outside, yeah, to the right wedge or the left wedge, right? So you are, yeah, right, and okay, and in this setup, there's a natural state, which is the Huddle-Hawking state. Which I'll call omega beta. It's at some fixed temperature. And it satisfies some nice properties. There, of course, is a time translation symmetry in the space-time, which, you know, this is outside of the horizon. When you go to the other universe, the time goes the other way, and it continues inside as well. But it's no longer time-like. But there's just some killing vector that looks a lot like the Rindler, the boost vector that we talked about before. And in particular, this Huddle-Hawking state is invariant under this boost and satisfies, correlation functions satisfy the KMS condition. So, you know, alpha t, which is just this boost acting on operators in the algebra, A, B are in this wedge. So the algebra in, say, the right wedge. So this, you know, satisfies KMS, which we talked about which we wrote down before, so I won't write it again. So that means that, this is this is a modular flow, right? So it's a modular flow for the modular operator associated to this guy, okay? So this is kind of like a Bisignani-Wickman theorem for the black hole. Okay, and in particular, again, we can write that modular flow as some integral of the stress tensor and that killing vector, which is just the time translation. Okay. So this is K, and delta is e to the minus beta K here. So there's a temperature, because there's an explicit temperature now. Good. Now, another thing that you sort of get from this, which is kind of clear, if you study correlation functions in this background, your correlation functions in frequency, you can take their Fourier transform, are continuous. So that's suggestive that you, again, have this type 3 von Neumann algebra. So this is going to be type 3. Type 3-1, right? Now, okay, so now all I've really described is quantum field theory on this background. This quantum field theory, should also include graviton fluctuations, in some gauge fix, but there's some special mode that I have not included. So we have to talk about that now. So, in particular, I can think about other solutions that have the same boundary condition. And in fact, they're the same solution, but they're going to be sort of thought of as different. So it's the same black hole solution. I just change what I mean by the zero of time. So I just think of the zero of time on the left as being up here, a little bit further up, and the zero of time on the right is over here. And if I do something like shoot a geodesic through the killing horizon, we'll come across over here, and there'll be a gap. And that gap is something that I can't get rid of, so there's some mode associated to that. So there's some time mode that I'll call T. So this is some preferred slice, and this is the slice that we're using to describe, say, our state. And in particular, this is the same spacetime, so I can do some diffeomorphism to move this down here, but it's a diffeomorphism that doesn't vanish at the boundary, and usually we don't, mod out by those. So in fact, it's some physical mode. Okay, so in particular, the space of solutions classically will have some mode T. And there'll be some conjugate to that. And in particular, the conjugate is not hard to see. It's just going to be the energy or the ADM energy, right? So the ADM energy is something you can read off from the metric fluctuations. So in particular, if I take the metric and I expand it near the left boundary, I should find in some coordinates, some fall off, times some field tau here, and then the ADM energy, which I'll call H left, because it's at the left here, is just some 1 over g Newton times some integral over that tau, with some numbers here. I'm not being careful about. Right, okay. And so this is a mode of the metric, but it's something that I actually turned off when I talked about fluctuations of the metric in that background. And so now we're going to turn it back on. In particular, it's conjugate to this. So when we go to the quantum theory, we need to sort of add a new Hilbert space to our description.
Sorry, Tom, can I ask a question?
Yeah.
I think I know the words around it, but still let me ask. So if we also move TR upwards, the T right, here, then naively, that's also a large diffeomorphism that's independent of the left. So if we are using this diffeomorphism logic, shouldn't both of those be modes that we should count? Now, I understand there's a symmetry that you can pull it back.
Yeah.
But that's a state dependent statement, right? It's a symmetry only of the Hartle-Hawking state.
Yeah. So I think the answer is you could, but then there's an extra constraint you have to impose. So you could include a mode over there, and that's fine.
What's the extra constraint?
It's just this h left minus h right is k, right? So this is just a constraint that will actually do something non-trivial when you have the two modes. Yeah, so this is just the gravitational Gauss's law that you should impose. So yeah. Well, if there's no matter, yeah, that's right. So this is k is the mod. So I'll talk about this, yeah, if I have time. Yeah, you're not happy, Raju?
Yeah, I don't understand. So this is some kind of constraint, you say? Why is this like a constraint? This seems like a definition of k almost, right? Or what?
Well, in this sort of description where you added sort of two things, I think it becomes a constraint, yeah. Yeah, because it's sort of not automatically true. So your Hilbert space is yeah, you have to impose some constraint on you.
So right now you're imagining matter or no matter for now?
Yeah, well, yeah, let's include matter, yeah. Yeah. If there was no matter, I would just have, this is equal to this, and there's just 1 degree of freedom here.
Tom, is it going to be really important for you that you don't have to, if you just look at the algebra on the right wedge, and if you're trying to get this type 2 cross product structure, then, it doesn't really matter, right, whether HL is independent or not? I mean...
Oh, yeah. In terms of the algebra, the description is the same. Yeah, that's right.
I mean, if you weren't in a thermophile double state where I'd done something scrambled to the right-hand side, all this would still go through, right? If I had like a unitary acting on the left, if I had some shock waves on the left, I think you'd still get a type 2 algebra on the right.
You're thinking about a different space-time? Is that what you want?
Yeah, so for instance, maybe I set off some shock waves on the left-hand side, like so it's not, it's not the Hartle-Hawking state, but it's something else.
Yeah, I see what you're saying. Yeah, that's fine. Yeah, it's not really important what's going on over here for at least one of the algebras. Right. I will be interested in the commutant, in which case it's probably important over there. Yeah. 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 Okay, but we're not going to do that. We're just going to have one mode. So I'll do it this way. Okay, so in the quantum theory, we had these two operators and their conjugate. So when we quantize, we'll have this, which means we just have some new Hilbert space of just quantum mechanics, right? This is just standard quantum mechanics. This is like X and P. And so our Hilbert space is L2 of R, which of course is just an infinite dimensional Hilbert space, right? So this is just a infinite dimensional separable Hilbert space. Okay, all right. And so in particular, this is our new Hilbert space. It'll be the old one, H0, because I didn't say that, but the Hilbert space of these quantum fields that I talked about, where these algebra act, are on H0. Yeah. See, which one? Oh, the X and P. No, yeah, they don't live on the horizon or anything like that. So this left one, as we'll see, you should think of as actually living on the left boundary. Yeah. T is not really associated to any, to the left or the right. Okay. All right, so this is good. Okay, so now we have to pick a wave function for this guy. We have to pick a wave function. And so let's use the HL variable, so that's like our X. So we need a wave function is a function of HL. And so what should we pick? Well, there's a natural choice, which is if you just think about a black hole, and you do some kind of like Gibbons-Hawking calculation of this cigar, then you can extract from this the density of states, and in particular, you would have some partition function, which looks like this. And so it's natural to pick this as your sort of the square of your wave function, at least proportional to it. Now, there's an issue with this, which I won't go into in lieu of time, but basically this wave function that you pick, we're trying to send g Newton to 0. Well, the energy itself is diverging. That's not such much of an issue. I can just subtract some average energy. This thing goes like 1 over g Newton. But then this thing that you're left with is still fluctuating at the order of square root of g Newton. So you can see that from this wave function if you do that more carefully. And so, sorry, 1 over square root of g Newton. And so this has some large fluctuations. And so this is not really a good mode to work with. And so usually you have to rescale this mode. When you do that, you sort of lose the physics of this mode. In particular, your algebra in that case is a little bit trivial, at least in the strict g Newton goes to 0. The appropriate algebras for the left are A of the left wedge tensors functions of this rescaled version, which I'll call U. So U is just H left. The average, which way do I want to do it? Here, times root gn. That's right. And so you just get functions of this, and then on the right, you have the same thing. This is A0 tensor functions of U, and these are just all commutative. So in fact, this algebra is type 3, but it has a large center. If I take, this is the commutant of this, if I take, you can check that. If I take the intersection, I still get this. So you get this big center. It's describing the energy of the black hole, the large fluctuations of the energy of the black hole. Yes?
Yeah, I guess I was confused a little bit about what you meant by we can or cannot have matter. So this modular Hamiltonian that we are discussing is for some scalar field that's living on a fixed geometry, right?
Yeah, or
Of some
graviton.
QFT.
Yeah.
And then this H left mode, I should not really think of it as belonging to that Hilbert space of that scalar field. This is some gravitational mode.
Yeah, that's right. Yeah. So the scalar was in the H0. Where did I write it? Yeah, so yeah, I forgot to finish my thought. Yeah. The scalar is here, and then that's this gravitational mode.
So then the gravitational mode sort of gets turned on at small but finite g Newton. Is that right? Like this tensor product structure will get relaxed at small but finite g Newton.
No, I think this in principle will still exist. I'm not totally sure. I want to take a strict limit, so everything is sort of okay.
Okay. Well, my question was, if you turn on now a small g Newton, you also have graviton fluctuations.
Yeah.
Are we forced to include them at the same time we add this H left into the game?
No, I already included them in here. Graviton fluctuations are here.
I see I see.
Yeah. So they're kind of like, I factored out one mode, which is, you might have called the graviton fluctuation, but it's kind of a 0 mode. And then otherwise, I've just quantized the rest. Okay. Well, no, as we'll see, what's going to change is what algebras I associate to the right and the left. Right? So this factorization is not, you shouldn't think of this as related to this factorization issue at all. Yeah. Okay, maybe I'm not understanding what you, yeah. So this, this will sort of be automatically imposed. Yeah. This, yeah. I'm not going to impose an extra condition. Just that's how I'm working. Yeah. Yeah. What's that? Yeah. This, I'm just going to use this actually as a definition of this operator. Yeah.
Say graviton, etc., you quantize them, and that's all part of X0, as you said. And then stuff can fall through the horizon, etc., but that won't change the Hamiltonian of, say, whichever side you're interested in. But I imagine, because the Hamiltonian just becomes the full gravity.
Yeah.
But this is some extra mode over and above that, right? Which only arises in some way because of kind of a relative.
No, it's the same mode, right? So this is the conjugate mode to the ADM energy.
Yeah, right. But I mean, it requires the two sides to define.
I
mean, that's why it's commuting. Why is it exactly commuting with all the other modes?
It's not commuting with all the other modes. So no.
Okay, but your Hilbert space is.
You mean with these modes? Yeah. So these are not going to be local. The operators in this aren't going to be local. So you can think about them, but they're just not local to regions. Well, some of them will, but won't be.
Why does this happen? I mean, why is it? So why do you get this tensor product?
Well, it's just because, this mode is somehow independent of the small fluctuations, right? So this is like, I have small fluctuations in this space-time, and then I can just pick different choices for this t, and they're sort of independent of each other. Yeah.
Is the idea that HA minus HR is unchanged by those small fluctuations, or what?
HL minus HR is unchanged. So no, K, this is an operator. So I haven't actually defined this equation yet. You forced me to say it already. This is in this Hilbert space. Yeah. So we'll see how this works. Okay. Yeah. So let me say a few more things, and then I think we can discuss. Yeah. Yeah. Yeah, so you're asking like, how do I pick the wave function for these modes? Yeah, so as I said, there's a natural choice, and I'm not going to make that natural choice. Yeah, because that leads to this sort of thing. So I'm going to just pick a different wave function for these modes, and then we'll see what we get out of that. So yeah, I mean, this sort of Euclidean path integral will give you a natural choice. So if you like, this is like the canonical ensemble. And I'm going to go to something that looks more like the microcanonical ensemble. Because I'm going to fix the energy to some narrower band than the canonical ensemble. So in particular, I'm going to pick wave functions.
One more thing. It's a little different, bigger than what the other guys talk about, but I'm bothered by this GN going to zero limit. The way you take a limit in math is that you take it small but very fixed, and then you study a smaller and smaller number with a topology. That's not at all what you have in mind. Right? So you really
No,
GN equal to zero.
No, I have in mind a limit.
Then you have to tell us what it is for small.
Yeah, so then I need ADS-CFT. So if you let me have ADS-CFT, I can tell you what it is. It's n equals 4 super-Yang-Mills. So there I can be a bit more precise about the limit. For now, I'll hand wave about it, but I do mean something like that. Okay, so good. So we pick some wave function for HL, which is just independent of G Newton. Okay, that's the choice. And that gets around this feature. So in particular, the fluctuations of the energy are going to be order 1 now. That's what we're thinking, around some very large average. Okay, good. Okay, so now we need this sort of this constraint, this gravitational constraint, which you can think of as some kind of Gauss's law for gravity. So HR minus H left is equal to K, where K is the bulk modular Hamiltonian, right? So it's this integral of the stress tensor for the quantum fields. So this thing decidedly lives in H0. Now we have to sort of, what we have to do now is we have to pick various algebras and associate them to the left and the right and see if we get some nice choice. Okay, so the first thing we do is we say we have our left Hamiltonian mode that I've defined, and so that's going to be in the left algebra. Has to be in the left algebra. The right algebra, I'm going to construct first. This is just one observation. It's going to be constructed out of quantum fields on the right. So these are the quadratic fluctuations localized to the right. And the right Hamiltonian. But if I look at this constraint, the right Hamiltonian is equal to just K plus H left. Okay? So my algebra is going to be A of R, just quantum fields in the right wedge, times functions of this combination, K plus HL. Right, so remember HL I realized as some operator acting on this L2 of R. L2 of R. And so that's where that lives. But to make it sorry, this is the left Hamiltonian. To make it the right Hamiltonian, I have to add in this modular Hamiltonian. Okay? And then, and then I do sort of weak closure. Yeah, so I haven't defined the left algebra yet. I'm just saying is in the left algebra, but there's other things as well. Okay, so this this is sort of already interesting. So firstly, let me make the observation that this Hamiltonian, this right Hamiltonian, does have the right physics, right? So it's a Hamiltonian on the right, and it acts on the algebra of operators on the right. So it acts on these quantum fields as you expect, right? So if I take an operator in the right and I conjugate it with this guy, T, the left thing doesn't act on A because A is really in this Hilbert space, acts in this Hilbert space. So the left Hamiltonian doesn't do anything, but K is the modular Hamiltonian. So of course it moves this operator. So this is the boost of the time shifted operator. Right, so that's what we expect the right Hamiltonian to do. So that seems like a sort of good consistency check. Yeah. This zero is just the quantum fields. Right, so this acts on this Hilbert space. Yeah. 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 Sandip. Yes, yeah. Yeah.
What does that mean from the point of view of the two boundaries? Why is there any kind of relation? They happen to be in atomic double space. Otherwise, the Hamiltonian
They are, and you'll see how it works. So yeah, I think you should think of this. So this is the right Hamiltonian, and the left Hamiltonian is HL. Okay. So those are the two Hamiltonians. It's this and this. Okay, and they are they commute with each other. That's right. This commutes with itself, so it commutes with each other. But those are going to be the two to the left and the right Hamiltonians. Okay? That's what we're going to identify in n equals to 4 super Yang-Mills as the Hamiltonians. Okay. Well, I took bounded functions. That's what this is. Yeah, I think it's pretty much exact. Yeah, it's the definition of HR. So yeah. You have to worry, yeah. So when you're imposing this constraint in the larger Hilbert space, you have to worry about that. But I don't have to worry about it. I don't know how to think of it in terms of laps. So yeah, I don't think. In this K? Yeah, there's nothing. Yeah, this is totally fine. You're saying, what if I pick a different slice to do this integral? This is a conserved charge. It's the same. Doesn't matter what slice I do it on. Yeah, it's just this operator constraint. That's it. Well, this, yeah, as I said, it's the same operator, so it doesn't matter. Yeah, so if this is the bulk quantum field theory, there's nothing interesting going on here. I think maybe you're focusing on the wrong thing. Yeah, so, okay, so let me try to finish, so say something that is somewhat-ish final. So let me say, yeah, this thing that I've constructed, this algebra is called the cross-product algebra. And it's usually written as follows. We got R. It's crossed with respect to the modular group, right? So there you write sort of an alpha, which is the generator here, and it's the modular group because of this K here. So this K lives there, and that's why it's the cross product. So it's the generator of that group. Good. So now, so that's the cross product. Let's just write down what the commutant is. So let me just tell you what the commutant is, and then we'll try to understand its physics. So AR prime is the set of the following operators. There's some representation, very similar to what we were talking about earlier, of the operators on the left. And then we need some functions of the left Hamiltonian, right? So we're including the left Hamiltonian. We have the algebra of operators for quantum fields on the left, but now we need this pi. So what is this pi? So pi of A prime, where A prime lives in here, is just conjugate by some unitaries that I'll call V, and V is just delta to the I, this T operator over beta. So this is this time shift operator that I defined that's conjugate to HL, okay? So this is the commutant. And so you can check, I'll let you check that that's the commutant. Now physically what's going on? So physically, what you should think of is in my first algebra, I didn't have to do anything funny to my right operators. So I just had bulk quantum field theory operators over here, and I didn't do anything. I didn't include this V or anything like that. So you should think of these operators as being dressed to the right because I picked this T to be shifting on the left. So these are sort of dressed in the sense that they have some clock associated to them, and that clock makes reference to the right CFT, or the right boundary with some time here. So that's the right algebra. And then the correct Hamiltonian for that had to be shifted by, it was this h left plus k, and we needed this k so that it actually commuted with those operators. Now, the left algebra here, if we tried to use a 0 w left without these v's, we run into some paradoxes, and partly the issue is that these operators are over here on the left, but you should think of them as being dressed to the right. Okay, so they're dressed to the sort of the time on the right, and so to make them, to switch their dressing, so they're dressed to the left, I have to conjugate by this v, right? And so this v then basically shifts your coordinates over here, so now you're dressing to this 0. Okay, so this makes total sense now, and this algebra of operators is reasonable that you would associate this to the left, right? So we just say that's the left algebra. And in particular, because of this dressing, this V thing here, the left Hamiltonian has a non-trivial commutation with this guy, and it just moves the operator as you expect. Okay, so it acts like the left Hamiltonian should. Okay, and so, yeah, so this is a cross-product algebra, and the final thing I'll say before I stop is that when you start with a type 3 and you take the cross-product with respect to its modular group, AR is now to infinity, so it's a type 2, and the way to demonstrate that, which I don't have time, 2 is to find a trace. So you can just write down a trace on this algebra of operators. It's not that hard. You can show it has this tracial property where you switch the operators. And then, then you can use the fact that you have a trace to define entropies. I didn't really talk about that. Let me just say one thing. If I did talk about relative entropies, but it's very natural to think of sort of von Neumann entropies as relative entropies with respect to the tracial state or the tracial weight. So when you do that, it's like putting in a maximally mixed state into the relative entropy, and what you find in, just for quantum mechanical systems is that is the von Neumann entropy up to a shift. It's just log k minus the plus the von Neumann entropy. So von Neumann entropy minus log k or something. Yeah, so no, it's log k. Sorry, it's, I'm confusing myself. But yeah, it's related to von Neumann entropy. This thing is equal to log k minus the von Neumann entropy. And so up to this constant, you can define the von Neumann entropy in this way. And so that's what, what people have done. And so you can try to calculate this thing, and some arguments I was going to mention. You can sort of calculate what this thing is for the trace in this setting, and you find that it reduces to what we expect. That it's just the generalized entropy in the bulk. Where to talk about generalized entropy, you have to sort of split things into von Neumann entropy and area contributions. And as I think Matt has talked about, there's some issue with how there's some issue with each of those, but when you combine them, you get something nice. And so this thing is sort of the result. This is what you should take as sort of the definition of the von Neumann entropy. It's always well defined in this continuum limit, and yeah. Okay. So let me finish there, and thanks.
Sorry,
okay.
There's one hand raised.
This is a confusion of mine. So most of what you're saying could be said about operator algebras of quantum field theory in the presence of time-like boundaries. So say you're doing quantum field theory in anti-de Sitter space and you're an operator algebraic person, you don't want to talk about gravity. You'll still have to, so usually you would say modular flow is a redundancy of description, it's just a symmetry of the state, right? Now because you have a boundary, the time on the boundary keeps track of it. So I'm kind of confused. How does this? Yeah, where did we say use gravity in this picture?
It's this mode that we had to add. That's a purely gravitational effect.
But in the presence of boundaries, you'll have to promote. You have to say that there is a clock on the boundary. In
Do we have,
boundary
sorry,
quantum field
we
theory,
don't have to do anything funny in quantum field theory.
you cannot. Yeah.
We can fix our coordinates and everything is good, right? So I don't think, I mean, you can choose to add this mode. That's fine. And, people have proposed that that's how you should regulate entropy, for example. Yeah, entropy. You just take your quantum field theory and add this mode and then define entropy in the type 2 effect. Yeah, you can do that. Physically, I guess it's less, it has less motivation. It's just to regulate the entropy, yeah.
I'm not talking about cross product in modular flow, but anyway.
Oh, okay. Yeah.
I have a question. Okay, sorry.
Yeah.
Somebody is asking? Okay, I'll ask. Thank you. So this T, the tracial state, ultimately this is allowing you to define the entropy, right?
Yeah.
So I think this is quite related to what he asked also, but ultimately if I talk in terms of physical sense, what aspect of gravity is allowing you to define this tracial state, which is ultimately changing the behavior of type 3 to type 2?
Yeah, it's this new mode that you introduced, and it's not just a mode. It actually acts on the algebra, right? So it has some non-trivial commutation with the algebra, and that's what defines this cross product. And because it's the modular action, this could have been some symmetry of this algebra, some other symmetry, and it may not change the type in that case. But because it's the modular action, you know that it changes the type.
Okay, and the other thing, you just made a comment that the entropy, when you do it this way, turns out to be a sum of area term and bulk matter entropy.
Yeah.
That follows from here itself.
Yeah, yeah. So it follows in a certain class of states. So there are these, what I've done is I've allowed the energy to fluctuate a lot, and that actually makes for non-geometric things, so that's harder to interpret. But if you then, make that fluctuate less and less by some amount, you can approximate this generalized entropy very well.
I have a question, Tom. Yeah, the question is, if there's no more.
Sorry, Suvrat.
Yeah, the question is, so this is the first order in 1 over n. This is the first non-trivial correction 1 over n, right? But when you go to higher orders in 1 over n, gravity couples in other ways. For instance, the metric appears in the OPE of two field operators because they're 3-point coupling and so on. So it's not just the Gauss constraint. So is it understood, how one should generalize the story if one wants to go beyond like first non-trivial order in perturbation theory?
So let me say one thing. So I tried to state it so it was at 0th order in perturbation theory. So that was why I had to do this funny thing with the fluctuations of the energy. So that's the first comment. So it's 0th order. This was sort of in Witten's original paper. You can take this as your starting point, where you allow for the canonical fluctuations, and then include perturbative corrections in G Newton. And then you get something that looks like the cross product. It's not clear, we could use von Neumann algebras and things like that because it may not be developed where you have like a perturbative expansion. So it's not clear that everything that I told you about von Neumann algebras actually applies in that case. But that's an interesting project to think about. And you're asking about then what happens when I go to higher orders. I think people are quite happy making the statement that this is an all order thing. I'm less happy doing that, but yeah, people think that it might be an all order thing. So yeah, even with the interactions you're telling me, it's just as long as it's perturbative, it's fine. Yeah.
Sorry.
Yeah. So yeah, I think it's I think you're trying to do things at a much like more sophisticated level. This is just perturbative expansion. I'm fixing gauges when I can and things like that. So yeah, I don't think there's this is kind of the only issue that you have with the gauge invariance, and that's it. And you can deal with that, like
Sorry, Tom. I think I have a question which is rather naive, but let me ask it again.
Okay.
So we started with A0 of WR, let's say.
Yeah.
I'm trying to understand what the cross product structure means physically. And just to understand it in very lowbrow way, I take some quantum fields, I quantize them in the bulk, and I construct, localized operators on the right wedge.
Yeah.
On the right wedge.
Yeah.
Okay. So that's AW of R, let's say,
Yeah.
in a simple way. But then is the point, the physical point this, that, these operators are not really gauge invariant when it comes to including gravitational effects. That is, you have to, connect them with the analog of a Wilson line all the way out to infinity. Was this what you had in mind when you say you have to worry about the dressing? And is the final algebra the gauge invariant version of the naive operators you might write down? Is this the point, or? So
I think there's a way you can make it that exactly, those words are correct. I tried to state it in a different way. So all of the operators here are gauge invariant. Everything is gauge invariant. The issue is, are they local? So is it local to the left or the right? Right. And so because of this constraint, that becomes a non-trivial question. And so, you say the words like dressing just because you want to make sure that they're local operators. But yeah, you can work from this other point of view where you have sort of two modes on the left and the right, and then you impose a constraint. And then I think that maybe is more along the lines of what you're thinking. Yeah, but I think like all of the operators in this Hilbert space are gauge invariant. That's just, that's a given to begin with. And it's just a question.
So gauge invariant to begin with, and yet there is some, when you include this one extra mode of the relative shift, you create an additional algebra somehow, corresponding to how you reference one or the other boundary for these gauge invariant operators to begin with.
Yeah, I think so. They're roughly like that. Yeah, sounds good.
Okay, it would be nice to understand what that referencing to the boundary means in a sort of more physical way.
Well, I think it is just this dressing. So I think this is sort of the way that I set it up. The operators on the right are sort of automatically dressed to the right, so you don't have to do anything with them. But because of this time shift over here, the operators on the left are actually also dressed to the right. And so I have to do something non-trivial to bring the coordinate for, to describe those operators back to over here. Right? So T here is like, in quantum mechanics, this is some, this is not an, this is some fluctuating variable, right? So it depends on the wave function that I'm working in. And so this is, So that's what this dressing operator does. This delta to the IT, right? It sort of, it boosts the operator relative to what T is, right, in your state. And so I think another thing to say is, if the fluctuations are quite big, these are it's a pretty non-local setting. So yeah, it's like, it's not really,
There are no more questions, and let's thank Tom for this wonderful set of lectures.